All right, good afternoon. So for video number 2, we're going to be talking about section 3.6, derivatives as rates of change. We already kind of saw the difference between 2 points and going from a secant line to a tangent line, but let's kind of clear this up and borrow some more ideas from physics to see exactly what we're working with. So the first section we're going to talk about is one-dimensional motion. So this just means we are moving in one dimension and maybe we can turn around and come backwards. And the question is, what does the position function actually tell us? That s of t equals f of x. What does that actually tell us? We've been working with it for a little bit. You've seen it in your homeworks and on the exam, but what does it really tell us? So here I've drawn a cartoon. We've got a house, and I'm going to say at time 0, our position is 0 if we're at the house. And in my little red sports car, I can drive down the road, and let's say I can only drive east, or I can turn around and drive west to get back home, but I can't go north or south or anything like that. So at time A, I'm at position s equals f of a. And if I let some time elapse, delta t, and I add that to time A, then I've traveled another distance, right? I'm further away from the house than when I started. So position is really important concept, and it's really fundamental in physics, but all positions are measured relative to a reference point s0. So it wouldn't make sense for me to say I'm 10 miles and then just end my sentence there. You need to be 10 miles from what? 5 miles from what? So in this case, I am position s equals f of a plus delta t away from my house where I started. And then it's important to talk about displacement. And the displacement is the difference between where an object currently is and where an object was as time elapses. And we call that delta S. It's the change in the position function. And this is going to be f of a plus delta t, that's our elapsed time, minus f of a. And you're probably really familiar with this because we've been using this in our limit definition of the derivative. So if we can talk about displacement and we can talk about a change in time, then we can talk about an average velocity. And the average velocity is going to be that delta S divided by delta T. So how far we traveled divided by the amount of time we spent traveling. So we've got F of A plus delta T minus F of A all over delta T. And this is exactly our limit definition, or our definition of the secant line, if you recall from a couple chapters ago. Now, we can always take the limit as delta t approaches 0 and get towards an instantaneous velocity. And that's v of a equals the limit as delta t approaches 0 of f of a plus delta t minus f of a, all divided by delta t. And we're taking that limit as delta t approaches 0, and that's going to give us our first derivative. So in this way, velocity is the first derivative of position. And it doesn't make sense to say, I'm 10 miles west from the house, and my instantaneous velocity is the derivative of where my position is. You have to have a position function. You have to have a position that also somehow encapsulates where you're going and how fast you're going. So if we can take one derivative, well, we can probably take another derivative. So the velocity at time t is v equals ds dt is equal to the first derivative f prime of t. And notice that we're using t's instead of x's because our time is our dependent variable. We can also talk about speed at a time t, and it's the absolute value of that instantaneous velocity. You wouldn't say that you're traveling negative 30 miles an hour. You would only say you're traveling 30 miles an hour. And then maybe you'd say west or east or north or south or along some sort of road. But completely correctly, if we can take one derivative, we can take a second derivative. And the second derivative of position, so the first derivative of velocity, is acceleration. So how much change is happening between two different velocities. And that's going to be a for acceleration equals dv dt equals d squared s over dt squared is equal to f double prime of t. So we can also talk about growth models. Calculus isn't only limited to what we can do in physics. We can also apply it to biology, economics, and many other fields that you'll see as you take more classes here at UW. So populations, prices, and a multitude of other things grow over time. You can imagine there's more people on the earth right now than there were during the Middle Ages, and there's more people on the earth during the Middle Ages than there were during the Mesopotamian times or during the Egyptian empires. So we want to measure that, and we can do that by calling P equals F of T. And there's always going to be some function that describes how populations grow. You might remember these explicitly, you might not remember these explicitly, but when they come up, just know we're talking about growth models. So if we can talk about growth, we can talk about the average growth rate of change, and that's just going to be delta P over delta T, and that's the exact same definition we had for average velocity from the previous slides. And if we've got a delta T in the denominator, we can always take the limit as delta T approaches 0, and that's going to be dp dt, so the instantaneous growth rate of change is equal to the limit as delta T approaches 0 of delta P over delta T. And that's the end of today's lecture.